In this lesson, we'll introduce continuity and one-sided limits. Let's first talk about continuity at a point and on an open interval. When we say f is continuous, that means f is not broken or uninterrupted. Basically, geometrically speaking, that means if you are tracing the graph of f, you don't have to lift your pen or pencil. Now, here in the following figure, we see three values of x at which the graph of f is not continuous. Let's take a look at the first one. First one, at this point C, at x value C, there's a hole on the graph. Therefore, you really cannot trace it, right? You have to lift your pen and jump through the hole, and then so that you can continue to trace the graph. So this is one example of discontinuity. The function is not defined at this value C. And the second type, the function f is defined as C. However, you can see that there's a jump over there, and which means the limit doesn't exist when x is approaching C, meaning that there's no fixed value so that f of x is approaching when x is approaching C from both sides. So the limit doesn't exist in this case. It's not continuous. Now the last example, the last case, the function is defined as C, however, and the limit exists. However, the limit is not equal to the function value, therefore there's a gap in between. So actually, the continuity at x equals C can be destroyed by any one of these three situations. And it's summarized here. The first scenario is the function is not defined at this point C, which is demonstrated in the first graph. The second type is the limit of f of x does not exist at x equals C, which is shown in here. There's a jump in this case. The limit of f of x exists at x equals C. However, it is not equal to the function value f of C, which is demonstrated in the last graph. And here, if none of these three conditions is true, then we can conclude that f of x is continuous at C. So now, after this little introduction, I believe we are ready to introduce the formal definition of the continuity. And the continuity at the point, let's first look at this case. We say a function f is continuous at the point C if the limit of f of x when x is approaching C is equal to the function value at C. If f is not continuous at this point C, then we call this point as a discontinuity. Now, extend this a little bit. We can define the continuity on an open interval. A function is continuous on an open interval a to b when function is continuous at every single point inside this interval. A function that is continuous on the entire real number line, negative infinity to infinity, is everywhere continuous. Later on, after we introduce the one-sided limits, we'll introduce the continuity on a closed interval. Now, this definition, actually, the continuity definition implies the following three conditions here. First of all, we see that in this definition, there's a f of C, right? That means f of C is defined. Second, we also see that the limits here, that means in order for you to have continuity at a certain point C, the limit must exist. And the third, these two must equal, so they are equal. So basically from this definition, we have the following continuity checklist. One, it is defined. Second, limits exist. Third, they must be equal. So therefore, when you prove something, a function that is continuous at a certain point C, you just have to check these three conditions. Discontinuities fall into the following two categories. One is removable, the other one is non-removable. When we say a discontinuity at C is removable, that means f can be made continuous by appropriately defining f of c or redefining f of c if f of c has been defined already. Now, for instance, let's look at the graphs that we have seen earlier. This first one, this is a removable discontinuity because we can actually define f of c, like define f of c to be this value, right? You define it, okay? The second one is also removable because even though f of c is defined, we can redefine it. If we can redefine it so that f of c is equal to that value, then the discontinuity will be removed. However, for the last case, regardless how you define f of c, there's no way that you can fill in this jump. So therefore, this is the example of non-removable discontinuity. Let's do some exercise here. Let's take a look at the problem number 1. Here we are given a graph, and then we want to categorize or identify the discontinuity and also the type of discontinuity here. So we're going to look at the interval from 0 to 7 inside this interval. And then graphically, we can see that there's a hole there. And then it's not continuous here, right? And also there's a jump here. And also right there, it's not defined as well. So therefore, we can see 4 discontinuities in the interval 0 to 7. So let's quickly write this down here. So we have f has discontinuity at the following points: x equals 1, this is 2 here, this is 1, 2, 3, and 5. Simply because there's a hole here, there's also a gap here, and then there's a jump here, and it's not defined there. It's pretty straightforward there. Now let's take a look at each one of those. So f of 1 is not defined, right? There's an open hole there. Therefore, it has a discontinuity there. For the x equals 2, the limits actually exist, which is actually equal to 1 because they're both approaching 1 there. And f of 2 also defined, which is 3, but they're not equal. So therefore, it is discontinuous. Discontinuous at x equals 2 because they are not equal. And when at x equals 3, we can see that the limit x approaching 3 does not exist, right? Does not exist because the left limit, the left side is approaching 2 and the right side is approaching 1. There's no fixed number that f of x is approaching from both sides. So therefore, it doesn't exist. Therefore, it's not continuous. And at x equals 5, we can see that neither limit exists nor the function is nor f of 5 exists. So therefore, it's a continuous. Now let's see which one is removable, which one is not. We can see that this one is removable because we can redefine f of 1, so redefine f of 1 to be 3 so that it's connected. And we can redefine f of 2 to be 1 so that it's connected. For the other two discontinuity, because the limits do not exist, therefore they are non-removable. So we can quickly write this down. Removable discontinuity at x equals 1 and 2, right? Now let's look at another example here. We have several functions given, and we want to discuss the discontinuity of each function. So let's look at the first one, f of x equals 1 over x. Here the domain is all real numbers, right? All real numbers except x equals 0. That means, if you remember that, how do we evaluate the limits from previous lesson? When this function is defined in its domain, we do the substitution. So in other words, limit x approaching c f of x is actually equal to, and this is a rational function, right? So it's actually equal to f of c when c is in its domain. When c is in its domain, right? When c in domain. What that means is, do you see that's actually the continuity definition, right? So therefore this is true. So in other words, we are going to say f of x is continuous on negative infinity to 0, and also from 0 to infinity, right there. And what happened at x equals 0? Well, if you look at the graph of 1 over x, which is something like that, and we can see when x is approaching 0 from both sides, and the function value is approaching either infinity or negative infinity there. So the limit doesn't exist. So at x equals 0, limit it does not exist. And therefore, this is a non-removable continuity. So it is a non-removable discontinuity. All right, now let's take a look at the second example. The second example, again, the domain is everything except x equals 1, right? So basically negative infinity to negative to 1, and from 1 to infinity. Therefore, the function is continuous on its domain, so on these two intervals, and so continuous on these two intervals. Now, let's look at what happened when x is approaching 1 at x equals 1. Let's look at the limits when x approaching 1. That means when x is very close to 1 but not equal to 1, right? Because x not equal to 1, we can actually cancel. So we factor the top, and then we can cancel this common factor, and then we can do the substitution equals, and then we can plug in 1, and then which is 2. In other words, the limits exist, but the function is not defined when x is equal to 1. Because limits exist, we can conclude that this is, so g of x has a removable discontinuity. At this x equals 2. And now you can actually look at the graph and verify that, right? So this graph, the graph of this guy is actually identical to the graph of x plus 1, except at x equals 1. So when x equals 1, it's not defined. So therefore, there's a circle, and you can see that it's a removable discontinuity. Now let's take a look at the next function g. So this one, this is identical to that, but I'm gonna add another part. Here, when x is not equal to 1, that's identical to that. When x is equal to 1, I'm gonna define it to be 2. And from the existing, what we just did here, we can see that the limit when x is approaching 1 of this function is equal to 2. And in this new defined function, when x is 1, this is 2. So basically, the limit x approaching 1 is actually equal to 2, which is g of 1, right? Which is equal to 2. And because the limit is equal to the function value when x is 1, so therefore, this actually, we can conclude this new g of x is continuous everywhere on the entire real line, negative infinity to infinity. So you can see that they're the same thing, but I define a function at this point, x equals 1, then now it's continuous. So therefore, there's no discontinuity here. In the next video, we'll talk about the one-sided limit.